Effective end-to-end data transmission relies on a dual address system working across different network boundaries. Misunderstanding how local hardware identifiers interact with global routing markers leads to systemic packet loss and addressing conflicts. To optimize data traversal, we must analyze the operational split between MAC addresses and IP addresses. A media access control, or MAC address, acts as the immutable physical identifier of a network interface card, functioning exclusively at layer 2 of the OSI model. Every hardware manufacturer burns a unique 48-bit binary value into the non-volatile memory of the controller. This flat addressing space is divided into an organizationally unique identifier and an extension identifier, ensuring no two physical devices share the same signature globally. When data moves across a local network segment, local switches evaluate this physical token to govern hardware-to-hardware delivery within the same immediate broadcast domain. The data flow travels natively via Ethernet frames directly from the source transceiver to the target transceiver. Because it contains no geographic or network topology hierarchy, a MAC address cannot route traffic outside its local broadcast boundary. It represents a strict point-to-point identification system tailored for immediate Layer 2 node adjacency, relying entirely on physical proximity to successfully execute local data exchange. To bridge separated subnets and span across global networks, the infrastructure relies on the Internet Protocol, or IP address, operating at Layer 3 of the OSI model. Unlike the flat, immutable physical identifier, an IP address is a logical, hierarchical address dynamically assigned to a network interface by administrators or DHCP services. This structure is split into two critical components: a network prefix that defines the device's location within the global topology, and a host identifier targeting the specific endpoint. Because it embeds this spatial layout, an IP address allows intermediate routers to evaluate and compute optimal data paths across multiple networks without caring about the underlying local hardware. The data flow moves through successive logical gateways, where routers look at the destination IP network bits to perform structural path determination. This logical routing architecture decouples data payloads from local physical media, providing a scalable framework that allows communication across completely distinct physical infrastructures around the world. Now that both operational frameworks are defined, we must evaluate their performance under stress conditions, where a systematic benchmark exposes their vital synchronization during data packet encapsulation. When an endpoint initiates an off-network transmission, it cannot directly wrap the payload using only the remote host's IP address. It must resolve the next hop hardware pathway. The system initiates an address resolution protocol, or neighbor discovery query, to map the logical IP destination to an immediate physical MAC address. As the data payload descends the network stack, the Layer 3 IP packet, containing the static, unchangeable global source and destination IPs, is nested inside a Layer 2 Ethernet frame. While the IP headers remain identical throughout the entire journey across the internet, the outer MAC address headers are stripped and rewritten at every single router interface hop. This means physical addresses are transient, changing with every local segment transit, whereas logical addresses remain persistent from end to end. Misconfigurations in this mapping stack stall routing engines, trigger broadcast storms, and break system-wide network convergence. Ultimately, local physical tracking and global logical routing must seamlessly integrate to maintain stable data paths. When troubleshooting complex subnets, do you prioritize verifying the Layer 2 MAC binding table or checking Layer 3 routing protocols first? Post your engineering analysis in the comments below and subscribe to execute the next protocol.